Perfect. Okay, so I will start the presentation. Hello, my name is Daniel, and I'm here on behalf of SEA.AI, and I make a presentation about using VLMs to navigate the sea of data. Obviously, a very good pun with the company name. And before I start the presentation, I will just thank Jimmy for the invite for this presentation, and also Kevin from SEA.AI to make this link, and everyone in the audience that is present. I'll just go through the agenda first. I will start with who am I and what we do at SEA.AI. And so you can have a bit of a context, what was our problem in the beginning. Then I'll go through the problem statement. After that, I'll go through our approach and some of the results to solve this problem. And at the very end, I have a small demo to show you. And at the end, if there's still time for it, there's a Q&A. So please leave your questions for the end. So without further ado, I'll just talk about a bit about who am I. And yeah, I'm Daniel, I'm Portuguese, and I have a master's degree in electrical engineering. I am very passionate about data and sports, and I've been a data engineer at SEA.AI for 4 years now. And I had the pleasure to work on various different projects and topics about this very complex topic, which is the high volumes of data. And yeah, what do we do at SEA.AI? I'm sure by the name you figured out already. We use AI to make the maritime navigation safer. And how do we do this? In our projects, we have a bunch of cameras for different customers and different use cases. But these cameras go on top of the boats, and then we use AI to basically detect everything on the surface of the water. And what happens is that we detect, maybe I can play the video so you can have more or less a description of this. We have RGB cameras and thermal cameras, and we have a detection model detecting everything on the surface. And the our main strength is actually detect the objects that are not detected by any other sensors, like the radar or the AIS, like wooden logs, small boats, fishing nets, whales, for example, fishing buoys, objects that can be very small or not, but crashing into them could put a lot of the people on board at risk. Sorry. Okay. And here is just one more use case. There's also the use case of the surveillance and also to rescue people in the water. You can see here during the night, our thermal camera and our detection model behaves quite well and quite consistently at detecting this human in the water. This is one of the use cases in our company. And one very hot topic at the moment as well is the whales, because being on a boat and navigating in the ocean, we're not really in our environment. This is someone else's environment. And yeah, ideally, we would like to detect this kind of objects in the water or at the surface of the water so we don't crash into them. And we keep safe the whales and also the people that are on board of the boat. And as you may or may not know, or most of you know for sure, the secrets for this is data. We have to have data to train our detection models to be able to detect these objects on the surface of the water. And you can see the 51 app right now. This is more or less how it looks in our database. We have a bunch of videos, RGB from totally different cameras. And what we do with these videos, we annotate them with bounding boxes. And these bounding boxes have a class and an ID of the object. And this is more or less how it looks in our database at the moment. Apart from the bounding boxes and the classes of the IDs, what we also annotate is, for example, metadata. So the region where the videos were recorded. Is it shoreline? Is it open sea? And also the weather. If it's sunny, cloudy, foggy, rainy, all of this metadata, we also annotate it. So what is our problem now? You might have figured out already. What we struggle the most sometimes is the decisions that we make in the past that haunt us in the future. And for us, it was our annotation strategy. So we started by annotating bounding boxes and not a lot of extra information apart from the region and the weather. So we don't have information like, is the object approaching? Is it moving away? Is it in collision course with us? Is the camera mounted on a boat or in a land installation? Are the objects moving at high speed or stationary? So we could obviously annotate manually all of this information, but this takes time and money that ideally we would not like to spend. So to have this information, what can we do? So is there anywhere a model that can do this for me instead of having to waste time and manually annotate it? So that's why we looked at the vision language models, or VLM. And VLMs are basically advanced AI models that combine the abilities of vision and language models to handle both images and text. These models take in pictures along with their text descriptions and learn to connect these two. So the vision part of the model captures details from the images, while the language part of the model understands the text. So this kind of teamwork allows the VLM to understand and analyze both images and text. And obviously, we want to know how good these VLMs are, or these models are, comparing with the human. And that's why we have these benchmarks that are widely known and are public. So for this specific problem, we chose the multi-model evaluation benchmark of multi-model large language models in video analysis. So this benchmark basically tells us how good is a VLM at understanding the context of a video. And for this, this benchmark has a lot of diversity in the video types, as you can see here, a lot of durations, and then assesses the performance of the VLM in a bunch of different tasks and gives us a result compared with a human. There's a lot of videos in this benchmark, about 900. So we looked at the leaderboard of this benchmark to see, okay, is there any model that I can use that has a good performance? So for this, we looked at the top of the leaderboard, and we found Gemini 1.5 Pro, which is a model made by Google. And then earlier this year, it was said also, not officially on the benchmark, but Gemini or Google said that the Gemini 2.5 Pro was the model that surpassed actually the current leader in this benchmark. So we went ahead and just did some experiments with this model, the 2.5 Pro. And you can see here some experiments we did in the beginning. So this is a video from our database, a thermal video of a very big container ship just moving away from the camera. And we asked as a prompt, is this object moving away, approaching, or going from side to side? And the answer was, it is moving away. And you can determine this by, the ship appears to be progressively smaller throughout the video, which indicates it is increasing in distance from the camera. And after I asked, okay, can you tell me if the object is sailing at low, medium, or high speed? And then the VLM answered, okay, it appears to be moving at low to medium speed. So it's quite a good experiment, quite a good assessment from the model. So maybe we can just continue with the experiments. Apart from the moving objects, I also want to know if the object or the VLM can understand the weather. So for this, I uploaded a very foggy RGB video, and I gave as a prompt, what's the weather conditions in this video? And the answer was, the weather conditions in this video appear to be foggy or misty with overcast sky. So again, quite a good assessment, and that's why we went ahead with this model. So now that we have these first experiments with the VLMs, we can make a general approach. How can I, from a user input, I am the user, I want to find in a database, for example, a sailing boat that comes towards us. So the general approach to solve this is that we have the database videos in our database. We run them through a VLM with the appropriate text prompt, and then we have the video descriptions. But now I have to compare the video descriptions with the user input that I gave, right? So for this, I have to encode them first into embeddings vector. And then I can compare the embeddings vector of the user input with all the descriptions embeddings that I have in the database. And if I sort this by similarity, I have the most similar videos in my database. So this is quite a straightforward approach that we came up with. And for reference, what we are uploading as the database videos is 1 RGB. So I have all of the information about the weather, the state of the sea here, and then I have the thermal here, but with a bit of a twist. Now in the thermal, we draw on the annotations because I don't want the VLM to figure out what is the class of my object in the scene, specifically for thermal, because we already have the annotations for very small objects. The VLM in the beginning was quite struggling at detecting this and making this the right class. So now I just uploaded the drawn thermal video. So this is the general approach, right? And for this, first, to get the descriptions of the videos, we have to give a prompt to the VLM. And for this, we have this one, which is quite extensive, but it's really simple. I just said, okay, imagine you are a video descriptor. You are being given two videos, a thermal one that is annotated and an RGB video at the same scene, same time, exactly the same, but RGB. And then your task is to create a description with the following keys, combining information from both videos. So I want all of these information about the video. So I want the camera setup. Is it fixed on land? Is it mounted on a boat? The camera movement, is it static or panning? And then very important for me, I want the object and I want the class of the object. I want to know if it's close range, it's mid-range, far away, is it approaching, moving away, all this information, the speed as well, if it's slow, medium, or fast. And then I want also all these fields. I want to work on other conditions. I want the weather conditions, if it's sunny, cloudy, rainy, lightning conditions, which is day, night, sunrise, and sunset, and then the navigation region. I want to see if it's open sea, coastal, and harbor. And at the end, I want the collision risk. I want the VLM to assess if from the video, do I have any object coming towards me at the collision risk? And for this, I have the possible values of low, medium, or high. And I told the VLM, okay, be a bit conservative, but not too much. If any object is approaching at slow speeds, then the risk is medium. Just give me the JSON, nothing else. Don't explain why. You choose the values. Just give me the values in each key. And this is exactly what we did. We used the Google API to do this kind of workflow. But again, we uploaded the same video as I showed before, this container ship moving away. And now the output response was, okay, the camera setup is mounted on the mode. This is correct. The camera movement, it is static. And then we have the objects correct because it's a container ship at mid-range moving away slowly. We have the water conditions as well. It's choppy. It's cloudy during the day. As you can see here in the RGB, it's open sea, there's no coast, and the collision risk is low. This is a good assessment and a good performance from the VLM. And we also want to know if it's struggling somewhere. And in this specific scenario, it struggled quite a bit because it's a big motorboat coming towards us, but the VLM in the output says it's passing at medium speed, not really approaching. And in the collision risk, it said low because since it's passing, I'm not approaching the boat at high speeds or medium speeds or whatever. It says it's low. So this is not a good performance. And this kind of good and bad performance you can see in the results because we computed the description for about 670 pairs of thermal and RGB videos. But then we created a manual description for a small subset of it, about 50 videos or 50 pairs, to compare the difference between the VLM output and the human descriptions. And then we used the cosine similarity to compare the outputs. And you can see here the bar charts of the results, basically in a sorted way. So you can see that the VLM struggled the most at making sure at giving a good output for the camera movement, because if the camera is panning or if I'm just moving away, it's a bit dubious and it's a bit subjective for the VLM to figure out this. The collision risk was also sometimes didn't have the best performance because, again, even for humans, it's not completely objective to assess the collision risk to be low, medium, or high. Because someone that with a very good experience at sailing could say, okay, this is not really a collision risk for me. But someone that doesn't have any experience would say, okay, maybe I'm not really comfortable with this, so the collision risk would be high or medium, right? And then for all the other fields, the performance was quite comparable with a human description, apart from, the water conditions. Sometimes it struggled with figuring out if the water was calm or if it was in choppy conditions. and also some of the objects, as I showed you before in the previous example, it was not clear for the VLM to make the assessment if it's approaching or if it's passing by, not in collision course. So now that we have the results for this, now we have the descriptions for all the 670 videos. Now we have to encode them. And how do we encode them? We use the very known go-to Python module for using state-of-the-art embedding models, which is the sentence transformer. And the model that we used was the all-MPNet-based V2, which gives an output of the embedding. The output size would be 768. Another key point of this text encoding would be how we encode the description. So instead of creating one embedding per video, we created one embedding per object instance, and which is the sum of the embeddings for each video description field. So you can see here a 2D representation of each field of my description. So you can see here the region, it's coastal. You can see here the object. You can see here the collision risk. This is just an example. It's not really how it looks, the vectors. But yeah, just for the sake of the example, this is how it looks. And you can see here, then I just summed all of the embeddings from each field to a combined vector, which is this one in red. And I did this, for example, in one video. You can see here that I had 4 objects. Instead of creating one big embedding vector for the whole video, I create 4 different embeddings per object, which is this combined vector. And I do this because most of the time when I'm querying something from the database, I want to find a specific object from the scene. I don't want to find the entire scene, right? I want to find a sailing boat approaching at high speeds. I don't want to find a sailing boat approaching at high speeds. And then at the same time, in the same video, I want, for example, a container ship far away. So that's why we separated these embedding vectors in different objects. And as you can see here, if we sum all of these blue vectors, what it does is the sum of these vectors will be biased towards where the most vectors are pointing at, or the direction of these vectors. So here you can see most of the vectors are pointing towards this. So this is where the combined vector is pointing at. This creates a problem because ideally, I want to give more importance to the object and not the context of the scene. I want to find the object first and then all the other stuff. Ideally, I would like to find that as well, but I want to find the object first. And if I give an importance to the object with scalar multiplication, so now what I can do is imagine this is the container ship vector. If I give a scalar that's way bigger than the other vectors, what it does is I am summing this vector. So for example, if A is my container ship, if I give twice the size of this vector, when I do the sum A plus B, this A plus B will be facing towards more the A than the B. So I'm giving more importance to the A vector, so the bigger vector. And I can give you an example of why we did this. For example, in this scenario, I am P3, I'm point 3, and I want to find a motorboat at mid-range passing by at medium speed. And for the sake of the example, I have only 2 points in my database. I have a fishing buoy far away stationary, and I have a motorboat at mid-range passing at medium speed. So this is exactly the point I'm trying to get from the database. But if I compute the cosine similarity, we'll see that these two have a higher cosine similarity of 97, and these two have a lower cosine. So if I'm querying it and I want to find the most similar, this is the one that will be found. And ideally, this would not be the case. I want to find the object first. And this cosine similarity is basically higher because even though the object is not the same, all the other fields are the same. And for this point is the opposite. So the object is the same, but all the other fields are the opposite. So it's facing more towards what's most similar in the description. So that's how it happens. Ideally, I don't want this. I want to find the object first. So if I do the weighted embeddings, if I give importance more to the objects, Again, I am 0.3 now. I'm the motorboat mid-range passing by at medium speed. If I give importance more to the objects, this is the point I find first. So this is the point that has the highest cosine similarity in our database compared with this P2, which is 64. So that's why we did the highest with the weighted importance in the field descriptions. So now we have what we have. We have the descriptions of all the videos. We have how to encode them. Now we have to know how to search for them. So we have the user embeddings, and we have all the descriptions embeddings. So all the vectors in my database. So what I can do is I take this embedding and I compare this using cosine similarity with all the embeddings I have in my database. And then I can sort them out, and then I have the most similar videos. And we would do this by computing the cosine similarity, and we use cosine similarity because it is frequently used in semantic search because it effectively captures the direction of vectors representing text or other data rather than their magnitude. And this is particularly useful when dealing with embeddings, where the length of the vector might not be as important as the direction at which it points, which represents the semantic meaning. And you can see already a problem with this because we're just computing the embeddings for 670 video pairs. But what happens if we do this for thousands or millions of videos in our database, right? So this is how the workflow works. We have to generate an embedding for the scene. Then we have to compute the cosine similarity between the query and also every single one of the existing embeddings, and then sort them out by similarity. This at scale will be computationally a bit challenging. So to solve this, we used basically a vector database. And we use Python for this because it's built to efficiently store and manage and search on massive collections of high dimensional vectors. This is exactly what we are doing here. So now instead of comparing the embeddings with all of the embeddings of the database, I now first index the embeddings in the pinecone database, and I do the query with a bit more efficient algorithm, which Pinecone uses, which is the hierarchical navigable small world. So instead of comparing, what we do is we index the embeddings, and this indexing will make all the vector embeddings to be built as a graph, and then graph search is way more easy and way more efficient to search for and way faster for us. So at scale, this will work anyway, and the previous approach would not. So now that we have everything, we have the descriptions, we have the way to encode them, and we have a way to search for them. Now we want to build an interface with a user. And for this, we built a very simple Gradio app where on the left, we have all the input that I was telling you about before, all of the fields that I want to give the user to fill, basically. And in this example, I want a container ship far away, stationary. And yeah, I want the other fields to be daylight, it's coastal, collision risk to be low. On the right, this will appear to, yeah, the highest scores for the videos will be, yeah, the ones that are most similar to my query. So you can see in the first video, there was a container ship far away and stationary. In the second video, the score is a bit lower, but still the same scenario. And then the third video, and a 96 score. And after that, there was no more videos in the database at this specific time. So there's no more results for this. And you might be asking yourself, why did we use Gradio and not 51 right from the start? And the reason is because this in the beginning was made for another department in the company that would need a bit of a more user-friendly and not mess around with the main database. So that's why we use Gradio, but we are actually in the making of making a plugin for this directly in 51 for the research team or the data team in our company. So now that we have everything, we have the descriptions of the videos, we have how to encode them, how to search for them, and the interface. Now I can go and give you a bit of a demo of this app working quite well. And for this, the first use case I have for you is I want a sailing boat approaching a high collision risk. So for this, I have in my object to search for the sailing boat approaching, mid-range at medium speed, and then all the other fields. And at the end, I put the collision risk to be high. And when I click search, this is a very fast search of about even less than 2 seconds. Give me as an output some videos of the database sorted out by score. So you can see here that the first video with the highest score is actually a sailing boat approaching at high risk, because if you look closely, this sailing boat most of the time throughout this video is in the center of the image. So this means it's at collision risk. If we go a bit further, we also have another video of this happening. A score is a bit lower because, as you can see in the pixels of the video, this is a bit of a foggy condition. So this is not actually what we looked for. So, but still, since we gave importance to the objects, this video will appear. And the third video, yeah, kind of the same, sailing boat in the center of the image that we are navigating towards. So one more example that I have for you is I want now for, I don't know, surveillance purposes or a use case of surveillance, I want a human in the water seen from a land installation. So now I can choose the camera setup to be fixed on land and the objects to search for to be a human in water at mid-range and stationary. Yeah, collision risk is low. All the other fields, cloudy, calm conditions. And then you can see that the search was very fast again. We have a video of a swimmer in a land, filmed from a land installation, just going up and down and coming to the surface again. And then the second video is more or less the same from the same scenario, but still with a very high score because it's exactly what we want. If we want to show you one more use case, I want now the same scenario, but I want more of a search and rescue scenario. So I want a human in the water seen from a moving boat. And for this, I obviously change the object to search for again. And with this, I want a collision risk because I want videos that tell me there's a human coming towards you or I'm going towards a human. And for this, you can see again the videos in database. I just go forward in time, so you don't have to wait all of this time. But you can see here that we're going towards a human here. Just waving, saying hi. And the same for the second video, the very high score as well. You can see that there is a human that we're going towards as well in a collision risk scenario. So yeah, we have the third video, but it's more or less the same. We're going towards a human asking for help. And yeah, this is all the demo I had for you. If you want to go ahead and ask your questions.